Our planet relies on a delicate balance of gases in the atmosphere to maintain a habitable temperature. This balance, known as the greenhouse effect, is essential for life as we know it. Sunlight enters the atmosphere, warming the Earth's surface. Some of this heat radiates back into space. However, certain gases, namely carbon dioxide and methane, trap some of this outgoing heat, preventing it from escaping. This trapping of heat is what keeps our planet warm enough to support life. Without these greenhouse gases, Earth's average temperature would be a frigid -18 degrees Celsius. However, the concentration of these gases, particularly carbon dioxide, has been rising steadily since the Industrial Revolution. This increase is primarily due to human activities such as burning fossil fuels and deforestation. As carbon dioxide levels rise, so too does the amount of heat trapped in the atmosphere. This intensifies the greenhouse effect, leading to a gradual warming of the planet, a phenomenon we know as global warming. While the greenhouse effect is a natural and necessary process, its intensification due to human activities is causing unprecedented changes to our climate system. Deep within, the polar ice caps and glaciers lie frozen records of Earth's climatic past. These records, preserved in layers of ice accumulated over millennia, are known as ice cores. By drilling and extracting these icy archives, scientists can analyze the trapped air bubbles and reconstruct past atmospheric conditions. Ice cores reveal a striking correlation between carbon dioxide concentrations and global temperatures over hundreds of thousands of years. Periods of high carbon dioxide levels coincide with warmer interglacial periods, while lower carbon dioxide levels correspond to colder glacial periods. This historical data provides compelling evidence of the link between greenhouse gases and global temperatures. Furthermore, ice core data shows that current carbon dioxide levels are unprecedented in at least the last 800,000 years. This rapid increase in carbon dioxide, far exceeding natural fluctuations observed in the past, coincides with the period of human industrialization and the widespread burning of fossil fuels. The evidence from ice cores paints a clear picture. Human activities are altering the Earth's atmospheric composition at an unprecedented rate, pushing the planet into uncharted territory. The consequences of this rapid change are already being felt around the world. While natural processes like volcanic eruptions and wildfires contribute to the global carbon cycle, human activities have become a dominant force in shaping carbon dioxide levels. From the dawn of agriculture to the rise of industrial societies, humans have altered landscapes and released greenhouse gases into the atmosphere. Consider the Bronze Age, a period of significant technological advancement, but also one marked by widespread deforestation. The clearing of forests for agriculture and settlements across Europe released substantial amounts of carbon dioxide, contributing to a noticeable warming effect. Research suggests that deforestation during this period resulted in a 1.5 degrees Celsius temperature increase in Europe. Today, human activities continue to impact carbon dioxide emissions, both positively and negatively. While the burning of fossil fuels remains a major contributor to greenhouse gas emissions, efforts to mitigate climate change are also underway. Modern firefighting techniques, for example, are designed not only to suppress wildfires but also to minimize their environmental impact. By limiting the spread and intensity of these fires, we can reduce the amount of carbon dioxide released into the atmosphere. Understanding the historical context of human influence on carbon dioxide levels highlights our capacity to both impact and potentially mitigate climate change. The choices we make today will determine the trajectory of our planet's climate for generations to come. Volcanoes, often perceived as fiery agents of destruction, play a complex role in Earth's climate system. While they release carbon dioxide during eruptions, their impact on global temperatures is far more nuanced. Large volcanic eruptions can inject massive amounts of sulfur dioxide into the stratosphere, the layer of the atmosphere above where weather occurs. Unlike carbon dioxide, which traps heat, sulfur dioxide reflects sunlight away from Earth, leading to a cooling effect. This volcanic cooling effect can be significant, sometimes offsetting the warming influence of greenhouse gases for a few years. The 1991 eruption of Mount Pinatubo in the Philippines, for example, released so much sulfur dioxide that it caused a temporary global cooling of approximately 0.5 degrees Celsius. However, volcanic cooling comes with its own set of consequences. The sulfur dioxide injected into the stratosphere reacts with water vapor to form sulfuric acid aerosols. These aerosols, while reflecting sunlight, also contribute to acid rain, which can damage vegetation, contaminate water sources, and negatively impact human health. Therefore, while volcanic eruptions can temporarily cool the planet, they also highlight the interconnectedness of Earth's systems. Understanding the complex interplay between volcanic activity, atmospheric composition, and climate change is crucial for predicting future climate scenarios. Section 5: A World Awakened: Recent Volcanic Eruptions and Their Impacts. Recent decades have witnessed a surge in volcanic activity around the globe, raising questions about potential links to climate change. While attributing specific eruptions solely to global warming remains a complex scientific challenge, the observed increase in volcanic activity warrants careful consideration. The 2010 eruption of Mount Merapi in Indonesia, for example, was one of the most powerful eruptions of the 21st century. The eruption, which caused widespread devastation and loss of life, released a significant amount of sulfur dioxide into the atmosphere, impacting regional climate patterns. Similarly, the eruption of Eyjafjallajökull in Iceland that same year, while smaller in scale, caused significant disruption to air travel across Europe due to its massive ash plume. More recently, the Reykjanes Peninsula in Iceland has entered a new period of volcanic unrest, with multiple eruptions occurring since 2021. This heightened activity, marked by fissures opening in the Earth's crust and spewing lava, has raised concerns about potential impacts on nearby communities and infrastructure. While the direct link between these specific eruptions and climate change remains an area of ongoing research, the increased frequency and intensity of volcanic events serve as a stark reminder of the powerful forces at play within our planet. Section 6: Rising Tides, Shifting Earth, Sea Level Rise and Geological Activity. As global temperatures rise, melting glaciers and ice sheets are causing a steady increase in sea levels. This seemingly gradual process has profound implications for coastal communities and ecosystems, but its impact extends far beyond the shoreline. The added weight of rising seas is placing immense pressure on the Earth's crust, particularly along coastlines and in tectonically active regions. The added weight of water acts like a finger pressing down on a spring. This pressure can influence the delicate balance of forces along fault lines, potentially triggering earthquakes and volcanic eruptions. While the exact mechanisms are still being studied, there is growing evidence to suggest that sea level rise can influence seismic and volcanic activity. Furthermore, the rising seas are also encroaching upon and infiltrating land masses, altering the delicate balance of fresh water and salt water in coastal areas. This intrusion of salt water can impact groundwater resources and even affect the stability of underground geological formations, potentially leading to subsidence and sinkhole formation. The interconnectedness of Earth's systems means that even seemingly distant events like melting glaciers can have far-reaching consequences. Understanding the link between rising sea levels and geological activity is crucial for assessing future risks and developing adaptation strategies. Section 7: When weather becomes disaster, extreme events, and geological instability. Climate change is not only causing a gradual warming of the planet, but also increasing the frequency and intensity of extreme weather events. From torrential rainfall and devastating floods to prolonged droughts and heat waves, these events are becoming more common and more severe. While the human toll of these disasters is often the most immediate concern, their impact on geological stability is increasingly being recognized. Heavy rainfall can saturate the ground, increasing the weight on slopes and making them more susceptible to landslides. The added weight of water can also alter the pressure within the Earth's crust, potentially triggering earthquakes. In 2010, for example, heavy rainfall preceding the devastating earthquake in Haiti is thought to have contributed to the fault rupture. Conversely, prolonged droughts can dry out the land, leading to soil erosion and increased dust storms. The removal of vegetation and topsoil weakens the ground, making it more vulnerable to landslides and erosion. Furthermore, the loss of vegetation cover can alter the way water infiltrates the ground, potentially impacting groundwater recharge and increasing the risk of flash floods when rain does occur. Extreme weather events are becoming the new normal in a changing climate. Understanding their potential to impact geological stability is crucial for developing effective disaster preparedness and mitigation strategies. Section 8. A complex interplay projecting future geological activity and climate change. Predicting the future of Earth's dynamic systems is inherently complex, but understanding the interconnectedness of climate change and geological activity is crucial for assessing potential risks and developing adaptation strategies. While attributing specific geological events solely to climate change remains a challenge, the scientific community is making strides in understanding the complex interplay between these phenomena. Climate models project continued global warming, leading to further sea level rise, more frequent and intense extreme weather events, and potentially increased volcanic and seismic activity. The melting of glaciers and ice sheets will continue to add to the weight of the oceans, putting pressure on coastal areas and potentially influencing fault lines. The increased frequency of extreme rainfall events could trigger more landslides and potentially influence earthquake activity. Droughts, on the other hand, could lead to increased soil erosion and dust storms, further impacting land stability. The interaction between these various factors creates a complex web of potential consequences that require careful monitoring and analysis. Predicting the precise timing and location of future geological events remains a challenge, but understanding the underlying mechanisms and potential triggers allows us to better assess risks and develop strategies to mitigate potential impacts. The key lies in continued research, international collaboration, and a commitment to addressing the root causes of climate change. Section 9, a call to action, understanding and addressing the challenges ahead. The evidence is clear. Our planet is undergoing a period of rapid and unprecedented change, driven in large part by human activities. The consequences of climate change are far-reaching, impacting not only our atmosphere and oceans, but also the very ground beneath our feet. From rising sea levels and intensified volcanic eruptions to more frequent and severe extreme weather events, the challenges we face are complex and interconnected. Addressing these challenges requires a multifaceted approach that includes reducing greenhouse gas emissions, investing in renewable energy sources, and developing sustainable land management practices. But it also requires a fundamental shift in our perspective, a recognition that we are part of a complex and interconnected system. The Earth's climate, its geology, and its living organisms are all intertwined. Changes in one part of the system inevitably lead to changes in others. The future of our planet depends on our ability to understand these connections, to recognize the consequences of our actions, and to take collective action to mitigate the risks we face. The time for complacency is over. The time for action is now.